So we're going to give you a good deep dive today into both Vulkan and to SPIR V. And thankfully, you're not going to have to listen to me too much. But Tom is going to be comparing most of this. We're going to have a QA session at the end. But we have Tom talking about the working group. We have Graham, who's a specification editor on Vulkan. We have John, who's a specification editor on SPIR V. So we have the real people doing the real work here. So save up lots of tricky, in-depth questions for them, please. And then we have some demos and update reports from various members. So hopefully you'll walk out of here fully informed as to the state of the art of where we are in Vulkan. So I just wanted to spend 30 seconds kind of setting the really 50,000-foot context. I'm sure many of you are familiar with Khronos. We're the open standards organization. Any company is welcome to join. We focus on making open standard APIs that connect developers to cool silicon acceleration, like graphics, like compute, sensor processing, vision processing. And we have a good quorum of the industry, not just the hardware vendors, the platform vendors, but increasingly, and this is such awesome news, increasingly the developers and game engine developers are coming to the Khronos Group, leaning forward as we design these new APIs. So we're really making sure that these APIs are going to meet the needs of developers, we hope, for the next 25 years. And I think the Khronos Group is pretty well the only place where we could actually do something like Vulkan, because we have a quorum of the hardware vendors and the software vendors working around the table underneath a safe IP framework. So we actually had 3 announcements. We're not going to be focusing so much on OpenCL. We did that yesterday. Vulkan is the new generation API you're going to hear a lot about. SPIR V, though, I think, hopefully you'll come away from this session also beginning to understand how SPIR V can have a really fundamental impact on the graphics and compute ecosystem. In some ways, it's the hub of everything we do. It connects Vulkan and OpenCL, and it's going to enable a lot of innovation in the language domain. But Vulkan, like OpenGL, has been the foundation for many graphics over the last quarter century. Now we hope Vulkan can be the beginning of the next generation of APIs, and we need your help and we need your feedback to let us make that come true. So with that, I'm going to hand over to Tom.
Okay, so my name's Tom Olson. I'm the chair of the working group formerly known as glNext, and obviously been involved with the project from the beginning. I wasn't sure if we would get everybody in the room had already been to the morning session or nobody, and it looks like I got 50-50, which is the worst of both worlds. So what I'm going to do is try to just recap, because I'm assuming there are some people here who are not terribly familiar with what we're trying to do. All of you this morning, you know that. You saw the dump. So I'll try to go through it quickly, but in sufficient detail that the rest of the talk will make sense to you when we get to the nitty-gritty technical stuff. Committee history. I'm a committee guy. I love committees. I love history. There was, of course, a long period when people were aware that the GL franchise had gotten stale and needed a reboot, and it was years that we went in that condition. It was earlier last year, in June, July, that we realized that we had a critical mass of people who were committed and willing to work really hard to bring a new generation of graphics APIs to the cross-platform universe. We disclosed the project and what we were trying to do at SIGGRAPH. We had a few more members join then. And since then, we've been working really, really hard. She says louder, so is there a gain control? Because I have a limited capability to talk loud. Okay, is that better or worse? I don't hear any difference at all. Okay, I will project. So the status, we're not done. There's no spec. There is a provisional spec for SPIR V, but there is no API spec. We do have a huge amount of progress, and you're going to be hearing reports based on that progress. Bear in mind it's provisional, and we are evolving as things go. We have an internal header file, which we froze a while ago. IHVs are doing implementations. ISVs are targeting it. The reason we're not releasing it There are various reasons, but the dominant one is that the rate of churn is quite high, and we don't think it would be that useful to expose everyone to all that stuff going on. We are, thank you. Spec drafting is going on. Graham is the lead. Bill Lysia-Kane from Qualcomm is his co-spec editor for the API, and John tells me that the work on SPIR V is basically done, except for absorbing feedback. And there's some Vulkan-related stuff that changes. All the stuff for OpenCL is kind of done and dusted, and that's why they have a provisional spec out. So that is where we are currently in the project. So what's it all about? The vision that we started with back in June is we wanted a modern API. We needed something. There are all these modern APIs you're all aware of, Mantle, Metal, DX12, and I'm sure others in the pipe. But we wanted one which was cross-platform, which, and extensible, and had the good things that have made OpenGL valuable over the years. But it's a complete clean sweep. We started with nothing and moved forward from there. So we're not inheriting any legacy constraints other than the goals. Cross-platform, portable, efficient. So it's an architecture cleanup. It is multi-thread and multi-core aware and friendly. CPU overhead is greatly reduced. It is architecture neutral. We wanted it to be the same API for desktop and mobile. Mobile architectures are quite different. Almost all of them are tile-based renderers, where almost all desktop architectures are direct renderers. That's a substantial difference. We wanted an API which didn't expose more of that than necessary, but which worked equally well on both of them. And then I think our mantra all the way through it has been, it's an explicit API. It depends on you, the programmer, saying what you want to do at an appropriate time for the driver so that it can do its thing and doesn't make any guesses. One of the heartaches that we've had in recent years is the driver having to make all these inferences about what you're trying to do and fix things under the hood for you. We know that doesn't work terribly well, and so we're trying to get away from that. So this is my summary of the hour-long this morning that you missed if you weren't at the Valve session. So how do we get a modern architecture? Well, contexts are gone. We take the context in GL is both the place where you put state and build up commands, and it's also the place where you issue them. And you actually do it in one draw call, kind of. So those are separated now. You have command buffers, and you have dispatch queues, and you can have multiple of each, and you can access them independently from independent threads, and nothing bad will happen as long as you don't have two guys try to modify the same object at the same time. It'll all be glorious. This does put the responsibility for making sure that that constraint is obeyed on you, the programmer. We believe you know how to do that. We get low CPU overhead by taking all of the validation and error checking, which GL has traditionally done, and moving it out of the core API. So by default, the engine is going to assume that you know what you're doing and that you meant what you said, and that it'll work. And if you do something bad, like modify a texture while it's being rendered from, you'll get something on the screen, but we don't know what. And there are certainly plenty of opportunities for you to crash the driver. All of our members, all of our AHV members say they are now in a position pretty much to guarantee that you will not crash the system by doing that. And so that's why we felt free to have take this attitude. You can opt into validation, but it's explicitly as the layered mechanism that the Valve guys that John McDonald talked about this morning. But that is opt-in. We highly recommend opting in when you are developing. But once you think your code's bug-free, take it out. It'll run faster. And then the last key feature is that the application has much more explicit control of when work happens. So it's no longer the case. The driver is now incredibly discouraged, and it shouldn't have to take work that, when you specify the work, instead of actually doing it, it hides it and waits until just before you're ready to make a draw call, and then it goes and does all the work, causing a huge hitch in your frame rate. That's gone. There is a price for it. You have to tell the driver what it needs to know, when it needs to know it. There are API rules that say what that means. But if you do that, then all of the heavy lifting of compiling shaders and building up blocks of machine-specific state that correspond to the abstract API state. That all happens far away from your critical path loop, and it happens on another thread, which is cool. So that, in a nutshell, is what Vulkan is like. I'm going to sit down and shut up in a minute. I've got one more thing to say, and that is thank you. A lot of really bright people have worked incredibly hard to get us where we are, and my hat is off to all of them. I'm in awe of their smarts, because some of these are problems that I didn't think had solutions, but we found them. I'm not going to thank them individually. They know who they are, but we all owe them a great debt. I am going to thank one company individually. When we started this project, the first thing we had to deal with was, how do we get started? Because committees are really good at taking an existing spec and beating it into better shape. And they're really bad at coming up with a new spec from scratch. Designed by committee is a famous curse in the technology world. So we needed a place to start. And in the middle of that discussion, the folks from AMD came to about 2 weeks before our kickoff meeting and said, you need a place to start. Here's the mantle specification. You can start here, no strings attached. Use what you want. Please don't break it too badly. And so that was just an incredible leg up, and it allowed us to hit the ground running at full speed and make tremendous progress. So from the bottom of my heart, I say thank you, AMD. Please give them a hand.
Hi, I'm Graham Sellers. I'm in the light. I'm software architect at AMD. I work on OpenGL and now Vulkan. I've been representing AMD at the OpenGL ARB for quite a while, and I wrote a Super Bible, a bunch of other stuff. And the last year or so, I've been basically spending almost all my time on this Vulkan. I'm working with Bill Lysia-Kane on spec editing, yeah, this is the thing that I think everybody should use now. So what I'm going to do is I'm going to whip through really quickly a complete application from startup to teardown in Vulkan with a draw call and a present and all these kinds of things in like 15 minutes. This is pseudocode. They're real API calls from the header. We're not releasing the actual headers themselves, so there's some obfuscation in there. Mostly because, as Tom said, we're still finalizing some details and things will change. So if I tell you exactly how it works, it's not relevant because it's going to change. Okay, so the first thing you do is start up Vulkan. Each Vulkan as a whole is represented by an instance, and one application can have multiple instances of Vulkan. They're essentially independent, right? There's no global state, there's no global variables, there's no TLS variables or anything like that. This eases things like middleware that might want to use Vulkan for something. You don't need to worry about giving them your device pointers or anything like that. The instance is essentially the loader. We talked about that earlier in the Valve session. You can bypass the loader if you wish, but we would recommend that you don't do that. The loader aggregates all the drivers in the system, makes it look like one big driver with multiple GPUs behind it. You create your instance, you hand it some information about your application, and some allocation callbacks. All the memory that Vulkan needs will be allocated by your allocator, so you get to control your own system memory through that allocator. Once you have the instance, you ask it how many GPUs there are in the system. It will tell you the number of GPUs in the system and give you a handle to each one. And the handles are owned by the instance as well. And this allows you to see all the GPUs in the system. There might be multiple discrete cards from different vendors. You might have an integrated GPU in the CPU itself with a plug-in card. So explicitly talking to one GPU or another is part of the API. We're going to look into maybe resource sharing, at least between GPUs from the same vendor, but possibly across vendors as well, if we can work out the details. You can get information about the GPU. It'll tell you who made it, what it is, maybe the relative performance relative to other GPUs in the system, memory sizes, what kind of queues it supports, and also this cross-GPU compatibility. You can take two GPU handles and say, hey, are you two guys compatible with each other? Chances are, if they're identical GPUs from the same vendor, it's going to say, yeah, everything works. If they're totally different GPUs that don't know about each other, it'll probably say, no, it doesn't work. But we'll see how much cooperation we can get in there. Once you have a GPU, you create an instance of the device. And this represents essentially the stateful connection to the GPU. And when you create the device, you tell it how you're going to use the GPU. So the device creation information that you supply contains the number of queues and which types you want to use, which extensions you want to use. One of the problems we had in GL with extensions and extension hell is that you could accidentally use an extension without knowing about it. In Vulkan, you have to tell the device which extensions you want to enable, and you can't accidentally use an extension. And we as driver writers know what extensions you're trying to use. So if we see an application keep asking us to enable an extension we don't support, that's a hint that we probably ought to go implement that extension. You also get a level of validation. Validation is opt-in. The layers mechanism in the loader allows you to turn on validation layers, but also some validation information in the driver itself might help you. And the driver can expose multiple layers as well. So you can have multiple binaries with layers in, and they all hook together, and it's all very elegant. So once you have the device, you have queues. Queues are essentially where work happens. They're the scheduling contexts associated with the GPU. So it's kind of this two-dimensional grid of nodes where you have a number of families of queues, which might be graphics or compute. Each family has sort of capabilities. What you might have seen in Mantle as the universal queue is just a queue that supports compute and graphics. But different vendors might have compute-only queues or graphics-only queues and varying numbers of them. So you can say what kind of queue you want to have. And then each queue is completely independent of all the others. Any resource sharing across queues you need to synchronize, and things like memory residency is per queue. So these are essentially, they're probably part of the same physical device, but they're scheduled independently. The commands that the GPU is going to execute are put into command buffers. So you create a command buffer. It's just an object, an API level object. You can create as many as you want, fill them up in any order, and when you create the command buffer, you can tell the driver how aggressively you might want to optimize the commands in the command buffer and some other hints about how you're going to use this command buffer, whether it's going to be submitted once or over and over. So then you put commands into the command buffer. You begin recording the command buffer. You do one thing, do some other thing. It all goes in this command buffer. Every API takes the command buffer as the first parameter, and you can call this from any thread. Right? As long as you don't call into the same command buffer from two threads at the same time, you're good to go. You can build many command buffers from many threads at the same time. You end the command buffer. The driver does any finalization work it needs to do on the command buffer. This is where the heavy lifting happens. Right? So if you've gone wide in your engine, you have many threads, that heavy lifting work gets parallelized across all those threads. And even if you're running only on one thread, the API is so simplified, I guess, from a driver's perspective, the workload is much less for the driver anyway, so you're going to see some good performance gains from that. Okay, so shaders. We've touched briefly on the IR shaders. John's going to give a technical overview of the IR after me here. But basically, you create the shader. As much compilation work as possible goes on here. Validation of the shader bytecode and so on happens here. You provide that bytecode, and you create a shader object. We're going to use those shader objects to build pipelines. So the driver does as much work as it can here up front. And then those shaders get aggregated together with a number of other fixed function states into a pipeline state object. You have a graphics pipeline, you have a compute pipeline. As the API evolves, we may see other kinds of pipelines come up, configurations of pipelines. As much information as we can, we compile into this pipeline object. So this will include things like blend and depth, culling state, what kind of frame buffer attachments. Note, not the resources themselves. So you can change the frame buffers, but the pipeline state object, it says what kind of frame buffers you're going to be attaching, so the driver doesn't have to go in and patch shaders to export the right things at the right time later on. The whole idea of the pipeline is that it's ready to run, right? There will not be any last-minute patching of these pipelines. Some state can be mutable, but you tell the driver when you create the pipeline which bits of state you want to be mutable, so the driver can make accommodation for that. You can also serialize and deserialize pipelines, a bit like the get program binary that's in GL today. You can save and load the pipelines to cache them. The big difference being that once you serialize this pipeline, that's immutable. It's already compiled, it's ready to go. So once you load it again, there's no like finalization of the loaded pipeline last moment. So the mutable state is also broken down into blocks which get bound into these command buffers after the pipeline state object is bound. So for example, you have a dynamic viewport state, you have the depth stencil state, which represents whether the test is on or off and what the sense of the depth test is and so on. So you've told the pipeline, I'm going to be changing these things, then you bind these things into that pipeline object. Resources have kind of a CPU object, which is an API level object. And you create these things with like a create function. Again, you give it all the information you need about the resource, not the contents of the resource, but things like its dimensions and format and all these things. And that resource becomes immutable from much like an immutable texture in GL. So you can change the content of the texture, but you can't change its layout. But then the GPU part of that texture is also the application's responsibility to create and manage. You allocate memory for these GPU objects by asking the object what kind of memory does it need. So each object may require one or more memory allocations, and you can get the information about those allocations from the object. And then you allocate memory of the right type using allocmem call, and then you bind the memory to the object. And this allows you to, for example, allocate a very large chunk of memory and bind objects into that memory without making separate allocations for every one of them. It also allows you to do things like use the same piece of memory for two different resources if you know that those two resources won't be used at the same time in the application. Things like that. Then those resources are represented by descriptors on the GPU side. Descriptors are arranged in sets. Sets are allocated from pools, so you can make a little pool allocator. Each set has a layout. The layout might say, I have 25 textures, 2 samplers, and an SSBO, and so on in this layout. And so you create these layout objects. You specify when you create pipelines what the layout of the descriptors that you want to use is, and then when you create sets, you say what the layout of the set is. And these things become compatible. So you can switch pipelines and you can switch descriptor sets, and the driver will never cross-validate the two. It will just trust you that the layouts match and will dispatch your shaders for you. And so you can switch big swaths of resources very quickly. Change 300 textures if you want. The upper bound of the resource descriptor set is not small, I would say. So for each pipeline, you can have multiple sets bound, and what the sets are and the layouts of those sets is described by a layout chain. So now we get into rendering. So you have these things called render passes. Render passes represent information about what to do when the logical phases of a frame. So if you do multiple passing in your frame, these essentially encapsulate all the operations that you might do on a single frame buffer object. So you can't change the frame buffer inside the render pass. You specify which frame buffer you're going to apply the pass to when you begin it. So the render pass tells the driver what kind of frame buffer attachments you might have, what to do with the frame buffer when you begin and end the render pass, and this is vitally important information for deferred renderers and tiled renderers, but it's actually also pretty helpful for traditional immediate renderers because we know when to flush caches and these kinds of things based on the render pass information. So draws are always inside of render passes. So you begin a render pass in the command buffer, you bind pipeline, bind state, bind descriptor sets, you do your draw, then you end the render pass. The render pass information tells the driver what to do on the beginning and the end of the render pass. Everything's bound into a command buffer. There's no state, there's no context. The closest thing we have to a context is a command buffer, really. So all the draw types that we had in GL before, indexed and non-indexed draws, indirect draws, and compute dispatchers are all supported with this same mechanism. So you call VK command draw, do this, do that. and that goes into a command buffer. The driver will possibly do things like track redundant state within the scope of a command buffer. The command buffer itself stands alone. Driver doesn't know what order you're going to submit the command buffers in, so there's no inheritance of state from command buffer to command buffer. That's up to you to manage. Synchronization is through event objects. You can create events. You can set and reset them from both the CPU and the GPU side, and you can wait on them, and you can get their immediate status and find out if they're signaled or not. And also, when the command buffer is complete execution, they can signal fences, so you can tell when a command buffer is completed execution. For transitioning resources from one state to another, again, the driver is not going to track any state for you. If you try to, do atomic operations from a compute shader on a texture that's actually bound to a render target, bad stuff will happen. So you need to transition resources from one state to another. You do these things called barriers. They're basically execution barrier. All of the operations up to a point when you issue the barrier will complete, and then the barrier will happen on the resources listed in this barrier command. And that will allow you to do things like render to a texture and then issue a barrier which moves the texture to a readable state so that you can go render from it later on. If you get it wrong, we're going to render garbage. I mean, we don't try to track any of this stuff. We really can't, because you could render to a texture in one command buffer and then do a barrier on it and then read from it on the next command buffer, and we don't know which order you're going to submit those command buffers. So we can't track the state. It's just not possible. The validation layer will try and track that state for you. And if you try and read from a texture that's currently a frame buffer target or something, it will probably scream at you, hopefully. So once you have all these command buffers batched up, the resources bound into them, you know what the state of all your resources are, you can submit work into the queues. Like I said, these queues schedule the work onto the GPU independently of each other. What resource memory needs to be in GPU memory versus system memory, these kinds of things, is all per queue as well. So you have these memory reference tracking. You have to say this resource is going to get accessed by something on this queue. So you have these add memref, remove memref on the queue. And these are the memory objects that you use to back a resource. So if I have 25 textures in one big memory allocation, I add that allocation to the list for the queue. And then all those resources implicitly become ready to use. If you want to use resources across multiple queues, you can use semaphores on the queues. The queues can signal and wait on semaphores. So you know when one queue processes work, writes to a resource, the other queue can wait on it until it's ready to run. And that's how you get resources from queue to queue. Of course, if you're using different sets of resources, the queues can run in parallel and get most efficient work out of the GPU. Presentation is the process of getting the pretty pictures on the screen. The resources that you render to that can be displayed to the user are kind of a special kind of resources that they get bound to frame buffers as usual, but they're created and provided to you by what we call the Window System Interface, or WSI. Right now we're looking at trying to have multiple WSIs, basically the two major families of windowing systems. There's ones where the compositor owns the surface that you're going to present, and you have to get the surface from it. And then the other major family is where you create the surface and hand it to the compositor or to the desktop to show to the user. So we're going to try and divide all the platforms out there into these two major families and accommodate them like that. WSI also deals with going full screen, turning VSync on and off, telling what kind of display modes you have, multi-display, and these kinds of things. The presentation is enqueued into the queues along with the command buffers, and so you execute a bunch of command buffers and then enqueue the present operation on the queue, and pictures show up, which is awesome. When you're done, you're responsible for tearing down Vulkan. You have to destroy objects after you've finished using them. There's no implicit object lifetime, so if you've bound an object to a frame buffer and then delete the frame buffer, that doesn't necessarily delete the underlying objects, and if you delete an object that's still bound to the frame buffer and then render to the frame buffer, all hell breaks loose. You have to deal with that. There's no reference counting in this API. You don't want to call into the API through the loader and the validator to increment a variable. That's just silly. If you want to wrap these handles in smart pointers or something, go for it. Most of the objects are just destroyed with a destroy object call, and some objects, such as the device and the instance, are kind of special and have their own destruction calls, which tears down the driver. So what about AZDO? AZDO, for those of you who don't know, about this time last year at GDC, I presented with some of my colleagues about some techniques in GL to go real fast. And they do go really fast, but they're kind of hard to use. So what about AZDO and Vulkan? Well, Vulkan's very low overhead already. So we don't need to be quite as aggressive with the restrictions we put on the API. But so there are some key takeaways here. You can submit the same command buffer and over. So if you build a command buffer once and it takes so many milliseconds and then you submit it a gazillion times, the amortized cost of building that command buffer really does actually approach zero in a limit. Bindless textures, we've been debating the need to make bindless textures. Resource descriptor sets can essentially be unbounded. And you already have the make resident and no make not resident kind of calls that are there for bindless. So maybe we don't need explicit bindless. We have sparse textures. By binding memory to objects or not, you can effectively make the texture is not backed by memory. Multi-drawer indirect is in there. Shader draw parameters, all the stuff that makes the AZDO feature set is all in there. So yeah, Vulkan has very low overhead already, but all that other stuff is in there as well. So in summary, it's not really a low-level API. It's just a much, much better abstraction of the hardware we have today. It's very low overhead. Even if you don't go wide and use a gazillion threads, just using these APIs from one thread will really reduce the CPU overhead. We're cross-platform, cross-vendor. You're going to see demos from different vendors, mobile and desktop. We really wanted to make sure that mobile was a first-class citizen, hence render passes and all these kinds of things. It's open. Khronos is an open standards body. We want to see our specifications contributed to by all parts of the industry. We've had massive support as it is, but we want more collaboration and cooperation with everybody. All the extensions, we can bring them forward if they're still useful. And then SPIR V, I think we shouldn't underestimate what a massive impact on the compiler ecosystem SPIR V is going to have. So while I'm talking about Vulkan, the API, I think the coolest thing is probably SPIR V. So go write a compiler. It's going to be awesome. Okay, thanks very much.
Thanks, Tom. Yeah, I'm John Kesnick from LunarG, a senior compiler architect and language guy there. And I'll talk to you about SPIR V. Am I in the right places here? Click. Okay. So SPIR V is a new language. It's part of the SPIR language group from Khronos, which already existed. It has the same goals and high-level characteristics, which is it's a standard portable intermediate representation. Technically, it's a binary language. We'll talk a little bit more about that in a couple minutes. And I have pictures coming up that talk about these goals better. But the idea, of course, is that it's a hub, like Neil said at the beginning, that lets multiple high-level languages and compiler stacks target this one language and then distribute it as an intermediate file, and then multiple drivers can consume it. So we'll see some pictures of that coming up. Why do this? There's some negatives on the left with high-level languages and positives on the right here. Shipping source has the IP issue of you're delivering the actual source code of the cool things you did in your shaders, and shipping SPIR or SPIR V lets that get encrypted a little bit or obfuscate a little bit. It requires a tool to decipher, and if you need a tool to decipher your shaders, that's a level of IP protection. It improves portability. I'd like to talk a little bit more about that here. That high-level languages that we all code in have a lot of convenience features in them for humans, and rigorously specifying all those convenience features is very complicated, and different compiler front ends take different interpretations of what the convenience features were. An intermediate representation, because it's generated by a tool, allows a much simpler specification of rigorousness of what exactly is allowed and disallowed. So we get a big bump in portability. There should be a much smaller range of interpretation of what the right way to accept SPIR V is. And reduced compilation time. I think I have another slide coming up to talk a little bit more about that. I think the key thing there is that all your compilation time online doesn't just disappear. A typical thing that will happen on a driver is to still translate SPIR V into its own compiler stack and have to register allocate it and schedule it, and that will always take some time. So that's still going to happen. But obviously there are other steps that got offloaded. It'll depend on the stack what the ratio of those steps were. So SPIR V is a new intermediate language. It's made from scratch. It's fully defined and controlled by Khronos right now. It's not layered on top of another IR or an existing IR. And it's designed to represent all these weird things that show up in shaders and compute kernels natively. So, texture lookups, things like you can't move this texture lookup because it has an implicit derivative, and if you move it across an if then else, you changed what the derivative looks like. This stuff's all native and built into it. And there's a long list of weird things in shaders and kernels that are built into this that are, if you're layering on top of another IR, a little bit hard to express. So that's all in there. And the memory model is also interesting. GLSL shaders today don't have pointers, and that's very beneficial to compiler stacks to not have to be worrying about somebody do some sort of arbitrary math and add 12 to something and then dereference it and read memory. That's a big complicated part of compilers. It doesn't exist today in the GLSL stack. SPIR V is able to represent that stuff for languages that want to, but it has a mode it can run in that says, I'm not doing any of that weird stuff. It's just like the good old days of, this is the variable, it's allocated in memory, and we know it's there, and there's no weird stuff going on with pointers. As Graham said, SPIR V is the language accepted by the entry point in Vulkan. And there's not an entry point that says, here's a high-level language in Vulkan. That has to happen separately offline. This is the language. Now, Khronos is not dropping support for GLSL. GLSL is still a fine high-level language to target SPIR V with. It's just that's a separate step. Vulkan takes SPIR V. And similar story for OpenCL 2.1. So just talking a little bit more about the compiler chain being split in two. Presumably the normal way an ISV would use this is to offline translate shaders from whatever their favorite high-level language is to SPIR V. Can do some optimizations there. That form can be distributed to the end user, and on the end user, the driver finishes the compilation process. So main point is that the front end is not, I should actually say, is missing in the driver. The front end doesn't belong in the driver. But Khronos is looking at tools that still provide high-level language to SPIR V translation. So a little bit deeper look. This first bullet, I have a picture coming up. We'll look at that in the picture. One of the things that's in this language is that there's different ways of representing things. It could just be a stream of instructions that look like assembly code. It's higher level than that. It could have been an abstract syntax tree that front ends tend to make. It's a little lower level than that. This is the level of, you have a list of functions that are explicitly identified as functions. Each function has a list of blocks, basic blocks, and the blocks are organized into a control flow graph or a CFG. And we'll look a little bit deeper at something special in this language for CFGs. Another important characteristic of SPIR V is SSA form, which is single static assignment form. If you don't know about that and you want to know more about it, there's lots of information on the web about it. It's a pretty standard form to use in IRs these days that makes it easier for tools to work. And basically what's going to happen in SPIR V is when an operand is consumed, and I'm adding two things together and it says, here's the operand to add. That operand will have exactly one place somewhere else in the SPIR V module that says exactly what it is. And that lots of nice things fall out of that. So that's the form that this IR uses. Data objects, this is like constants. Well, I have a slide coming up that shows this as a picture. We'll get to that then. And the logical addressing mode stuff is what I talked about a little bit earlier. You don't have to, you can be in a mode where I'm not worrying about pointers, or you can be in a mode where you are worrying about pointers. It's easily extended. Basically, the SPIR V ends up being a collection of enumerations, and each enumeration has a bunch of tokens. These are easily carved up into multiple spaces that vendors or front-end languages can each have a piece of, and add their own enumerants to, and these things can be merged back together, so multiple extensions can be created simultaneously that don't conflict. And it's got debug information at line numbers, debug symbol names, all sorts of stuff like that, which are also trivially stripped out to reduce the size. So you can decide whether or not you're trying to keep the debug information or not keep the debug information. So we keep saying it's binary form. Here it is. That's the binary form. We're not going to read all the little words over there. The point is it's a stream of 32-bit words. The first 5 words are special header information, a magic number, the version number, a couple things like that. And then after that, it's a stream of instructions where each instruction takes a variable number of these 32-bit words. Each instruction starts by saying how big it is, how many of these words it takes, so that tools can really easily cruise through this form by skipping over instructions they don't know about or don't care about based on that initial size of the instruction. And that's it. That's basically the form of SPIR, or that is the form of SPIR. Now, it's not defined as a file format, but obviously you can just stick this directly into a file and use the magic number as a key for whether it's big Indian or little Indian. But the form, in memory form as a stream of words is what you'd be actually handing the API entry point. And that's what it looks like. That's how simple it is. That form then is the hub Neil was talking about. And basically, I think this picture is what almost all the information out about SPIR is really about. The richness that the ecosystem that can be built around it. And so I assume this is what people have heard about the most already. I'll point out just a couple things that might be less obvious. One is, in addition to lots of high-level languages, I have a laser thing. In addition to these high-level languages being able to target SPIR V can also target other languages. SPIR V has pretty high-level IR. It hasn't lost any information from the original source. That's really important. And so it can retarget another high-level language. And it can go back and forth kind of sideways here with other intermediate forms, other IRs. And OpenCL is used previous SPIR in the past, and it'll be very easy to convert previous SPIR to SPIR V and vice versa. So it's a form not just to be consumed by drivers, but a form to also translate to other IRs and high-level languages. And I think we're just discovering how interesting this picture will be, and people will be making new inventions and enriching the ecosystem as new ideas pop up on what this picture really looks like. So structured flow control, I'll touch a couple minutes on that. How am I doing on time? Doing okay. Okay. So I just have a couple more slides. So, it's kind of analogous to the pointer situation in GLSL. Another thing that happens with control flow is there's some easy assumptions to make because it's nested control flow. It's not spaghetti code. There's no go-to in GLSL. The nested control flow constructs like if, then, else, and loops and all that, they're nested inside each other. There's usually an escape out. You can do a return in the middle of anything. You can break out of loops one level. So minus those escape routes, those well-known escape routes, it's nested control flow. And that's really good for compiler stacks to be able to assume. And it's actually very important for some of the target hardware when you're doing SIMD-like things. I know we have much more fancy architectures now than SIMD. But SIMD-like things where it looks like your flow control diverged, and then you want it to come back together again to get everybody firing together on the same thing. So the real critical thing are these merge points And I highlighted this. This is, GLSL or C or C++, whatever on the left. This is a picture of a CFG with an overlay of showing how it nests. And on the right, this is a human readable form of SPIR V with labels and blocks and all of that. And the key thing is these loop merge and selection merge instructions, which are a way to declare right when you're about to start a loop or right when you're about to start an if test, that you are going to come back together again. All of your threads or all of your invocations, whatever your architecture calls them, will separate and then come back together at some point. So you declare where that point's going to be, and that, if you do it in the proper nested way, lets you never lose the structured flow control information through the stack, and that'll be good for the consuming target architecture. And I guess I'll take questions on stuff like that at the end of the session if there are any. But the point is, if you went to a normal CFG type IR, optimized it, the spaghetti code got remixed up to be different spaghetti code, you might have a bit of a problem on your hands for now targeting an architecture that wants nested structure.
We are probably, can you do 5 minutes?
Yep, no problem. I'm more than, less than that. So hierarchical types, I think the main point here is that this IR is high enough level that the variables haven't been allocated to some register set of 1,024 registers and with alias registers and flattened and all of that. In SPIR V, the real hierarchy of data structures is maintained. It's all logical, or some people say virtual registers. It's all logically represented still. So a structure here gets built up from the leaves up, and that's the SPIR V on the right. That all the types are parameterized. It says there's a 32-bit float type. From now on, 10 is a 32-bit float type. Now I'm making a vector of those. So 10, or 4 components of these 10s makes a vec4. Then I'm making a matrix out of that that's got 3 columns of that. It's just step by step, you build up whatever the data structures are that you want. And that's represented in the SPIR V. That information's not lost. So we saw the slide earlier summarizing. I think we covered all of these things. Yeah, we covered all these things. So last slide, call to action. It is a provisional specification, so it's subject to change based on your input. Let's have a discussion about what's good or bad about it, what should be added. These are the resources to do that through. I guess it's already been said before, go make a front end and do what you can on the back end. So thanks.
Thanks, John. That's fantastic. So we have a bunch of members who have ranging from I really like Vulkan, it's cool, to here's a demo running, and basically any sort of combination of those things members are welcome to do. But I have a list of them, and we're going to go through them one at a time, trying really hard to do 3 minutes each. So we'll see. If it doesn't work, it doesn't work, but we'll do our best. Our first speaker, Jesse Barker, my colleague from ARM.
Okay, well, so thanks, Tom. Right, so we don't have a demo per se. We do have code running on a prototype implementation inside ARM. And the reason for that is largely that we focused on the goals of Vulkan from the very get-go, which is basically to make sure that we could really give the developer back their CPU cycles. And we wanted to make sure that that was going to be effective on Mali hardware and convincing to do. And so we focused very much on that, as well as on the tiler pieces that Graham mentioned, the render pass, and some of the other bits of framework that were put in place so that tilers like Mali could make effective use of the information at the times when we needed it. So, to that end, we basically We have a prototype. It's not a driver you could download or anything like that. It's for investigational purposes. And again, just to confirm that we can deliver on any promises that Vulkan is making as an API and as an architecture. We picked, again, to some of the point that was made in the earlier talk today, we picked a platform that's out there today. Some of you, the phones in your pockets, the tablets in your pockets, have a chip that's pretty much identical to the ones that my partner and I used to do the prototype. And again, not that caveats are especially necessary here, given this situation, but basically, you know, we're reusing existing pieces of our current stack for ES, and kind of hacking things together to make them work properly, and so that again we can focus on the pieces of this API that we felt might, you know, we wanted to make sure that the Tyler piece of this was going to really come out cleanly. So our test case is the model you see over there, and it's 1,000 meshes, 3 materials, some number of state changes and all that. And basically we have 2 paths that go through that and draw that using ES and draw it using Vulkan. And we measure exactly how long it takes to build that frame of information using ES and using Vulkan. And the punchline, it takes us 1/5 of the time to build that frame on Vulkan that it takes us on our current OpenGL stack. And that's using equivalent features and functionality between the two. So we didn't do anything in one case that should have come out more optimal than the other one. We really tried to be honest with ourselves, and we had other people looking over our shoulders to make sure that, in fact, that's the way that it went. So we're very positive. I think this matches some of what NVIDIA showed in their demo earlier today at the Valve session. So we're happy. We feel like we're on the right track, and we think it's only going to get better. So thanks. That's everything I have.
Thanks, Jesse.
So my name is László Kisonti. We developed the GFXBench benchmarks, which are actually not just supporting OpenGL and Khronos standards, but are cross API for other APIs as well. And GFXBench 3.1 is our latest consumer benchmark, which has been just released this week. It is for OpenGL ES 3.1. It's a minor upgrade from 3.0 version. It includes compute shaders, and it's already freely downloadable from the Android store. 4.0 is our next version, which will come during the summer. It's currently beta stage, and it supports all the OpenGL ES, the Android extension pack. So it has tessellation, HDR, and physically based materials. You can see that these cars are originally actually only 140 triangles, and we dynamically generate these mathematical surfaces on the fly with tessellation support. There is no light max baked in. Everything is real-time calculated. And we already run this on some of the newer chips which support full Android extension pack. What we usually wait for is to have at least 3 platforms on the market, and that's the only time when we release it on the consumer side. And GFXBench 5 is only pre-alpha, not just because it's very new, but also the API was just announced this week, and it is already visible at the Intel booth. Down at the GDC Expo, and we plan to port this not just to Vulkan but DX12 Metal, and we will also have parallel ports to DX11 and the classic OpenGL ES to showcase what's the difference these new APIs are making in performance. And we also have a video. It's very short, but you will see what we try to set up. So this is it. It will be an alien-dominated scene. and obviously a lot of objects. This will be only released when, I think maybe next year, when there will be multiple drivers available on the market. So, cool. That's what it. Thank you.
Okay. So first of all, another thanks to Graham and AMD for Mantle. It was a great kind of inspiration for how we did Vulkan, and thanks to all of the other members who worked on the API. We're really happy with how it turned out. And some of the things we are most happy with is, for our architecture and for ARM and Qualcomm and some of the other toilers, that the old APIs are not a great map to what we do in our architecture. And Vulkan is a much nicer map to let you express your rendering problem in terms of what's going to happen in our hardware and the semantics of how that works. So Vulkan should let you do a much nicer, more efficient thing on tile-based architectures, as well as the kind of traditional desktop class IMRs and stuff like that. So along with things like the SPIR V, I think we really like the intermediate representation, the binary format. So helps us, the driver's much simpler as a result. We don't have to have a front end. And just the API, the attack surface of the API is very small, so that our alpha driver only took a couple of months to develop, 2 guys at IMG. Really simple, much smaller than our client API drivers or any other API. So, and one demo guy from my demo team managed to port an ES3 demo that we had to Vulkan in 2 months on and off, alongside the driver guys doing the driver at the same time. We took a cut of the header at the same time the Valve guys did, I think, and developed something against that, just to see what we were capable of in our hardware. And we have a working demo of that demo on Vulkan, and with pretty good performance. The main thing we saw was, with the demo, we weren't CPU limited, so we didn't go any faster on the frame rate, but we have much less CPU usage. The same thing that ARM saw, the same thing that NVIDIA saw, with the kind of the design goal of the API to just get out of your way, the CPU do more stuff. We have that in our driver, even after just a couple of months of implementation. So we're kind of, the goal of the API as we saw it, we're seeing it as early on as possible. So I hope we have a potential demo of the. We have a thing.
This is a HDMI.
Okay. So it's graphically complex. It's a physically based renderer. It's a forward renderer. Lots of textures. So 20 2K by 2K textures in this thing. But yeah, it's running at pretty good frame rate. It's a little bit lower than the ES3 version on the same hardware, but the CPU usage is just much lower, and for the kind of roughly the same performance. So we're managed to get something up and running in 2 months. That's the thing I really wanted to point out. The API is so simple that we can get a driver, 2 guys to do it in 2 months, get a demo ported, and everything just works. That's a testament to what Vulkan is as a graphics API versus what we have before. So we have it on our stand if you want to come and see it at GDC and talk about it a bit more. But thank you very much.
Awesome. Thanks, Reese.
Okay, my name is Sławek Gajewski and I work for Intel. I would like to present a very simple demo showing the benefits of Vulkan API. Okay, so this is a very simple application which renders 200,000 primitives. On the left upper corner, we can see the power consumption of CPU and GPU. Currently, we run in OpenGL mode, where we render about 30 frames per second. On the right upper hand and upper right side, we can see the CPU load, which shows that currently you're CPU bound. When we switch over the mode into the Vulkan mode, we can see some changes. So mostly we have higher frame rate. The GPU power goes up because we render more geometry onto the screen. The CPU power goes down. And what's interesting to see is that in Vulkan mode, we render, the application is multi-threaded, so the work has been split among multiple cores. And all this comes at lower CPU power. And I have another demo, if I can. Okay, so it takes a while. Okay, so this is live what Laszlo showed previously. This is the GFXBench, let's say, POC application running on Intel Windows driver. It's Vulkan version. Thank you.
Thanks, Slavek. That's fantastic.
So actually, I wasn't planning to come out here, and then it just so happened that yesterday I managed to get this demo together, and I really wanted to show this because it really highlights one of the biggest benefits of the Vulkan API over using GL. And the problem is with GL, with small draw batches and lots of mode changes and lots of program changes, it can be a big bottleneck. And I'm going to show how Vulkan does a much better job here. So this is a workstation benchmark that I think we have made this public. But this is drawing about 10,000 triangles. And this is with an unoptimized driver. We're doing about 35 milliseconds. Can you see that? Oh, you can't see that. We're doing about 35 milliseconds per frame. Now, if I modify it so that instead of batching draws by material, we actually just do naive drawing of all the material and all the geometry, you can see how the render time goes up to 143 milliseconds. This is mostly driver overhead. Now I'm going to actually switch programs between each batch of draws, and this is going to show the overhead of changing your program between draws and changing state as well. So now our render time's gone up to 400 milliseconds. This is all in GL. So now I'm going to switch to Vulkan. Vulkan is hosted by OpenGL driver, so we can easily just use Vulkan and OpenGL at the same time. In fact, all this UI is OpenGL. But you can see how we've gone from 400 milliseconds all the way down to 80 milliseconds just by switching to Vulkan, which is and this is basically a demonstration of the driver overhead and the API overhead that we're saving here. This is our Vulkan implementation isn't optimized yet, but just to get a taste of the speed of light, we have a version which uses the hardware much more efficiently, and with a lot more optimization work, we should probably get that down much closer to about 9 milliseconds, and that's compared to 400 milliseconds. But just remember, this is an unoptimized driver, so. But that's the kind of driver overhead that we'll be saving with Vulkan.
Thank you, Paris. Anyway, so Jens is sitting there. The Lunar G guys, in collaboration with Valve, have created a bunch of cool tools around the ecosystem, including the compiler work that John talked about. Are you guys working? You guys are working on the glaive also, right? Right. So the glaive debugger, there is a video of it in action. It's kind of a boring, it's not a cool demo unless you are somebody who actually has to debug code. But if you are, it's pretty awesome. But so we're not prepared to show it, but you can remember that, right? That's why it's in big print. So go and check it out and see the capabilities of it. And this is all built using the layering system, etc. Is John McJohn here? He's here. Do you want to say something, John, or do you want to show something, or shall we just? Good. Okay, we're good. So we're going. You've already shown great stuff. So I realize you don't have specs. Giving feedback's a little hard. There's a reason, as I said, we don't want to expose you to tons of churn, because then we'd be getting comments that we'd have like revision control, like what release are you running against when you asked us that question? And I think it would be an exercise in frustration for all of us. The SPIR V spec is there, and we have feedback forums for both of these. We absolutely promise to read everything that gets posted. We may not answer all of it, especially if it's just like, how does this work? Because sometimes the question may be out of date. It could kill us, and we're trying to get this thing done and shipped. But we are very interested to know your reactions, and particularly if there are things you obviously can comment on, like, have we missed some boats here? Have we, is there something philosophically strange or something we should be considering that we're not? We absolutely want to know that. I mean, you can tell us now, but if it comes to you later, use the forums. Khronos is an open standards organization. That means anybody who ponies up the cash can join. It's a small amount of cash, right? And sign an agreement that you basically bind yourself to certain kinds of non-friendly IP behavior. You promise not to do that. So you have to also execute that agreement. But as I say, things are happening fast, and we can always use help, and it'd be great to have you here. And last but not least, so we are not committing to a date because we want to be quality driven first, not schedule driven, but we are fully expecting to have initial specifications out before the end of the year. So stay tuned.
Does anyone have any questions that doesn't want to kick off? All right, let's do it. Yeah, thanks.
Hi, so I'm just trying to wrap my head, this is probably a question for Grant. Trying to wrap my head around the idea that there's a single API and multiple GPUs, and when does the IHV code kick in? So I'll give an example. You have VKQ submit. Let's say I have an Intel integrated chipset and an NVIDIA one in my laptop. So I'm submitting a queue to that. Who is responsible for implementing the first thing I step into when I go into that call?
So there's a loader which will dispatch for you. So VKQ submit is gonna, if you're using the loader, it's going to land in the loader, and then there's a dispatch mechanism which will then jump into the right driver. So very likely the instructions executed will be a dispatch table dereference and then a jump, and then you'll be in the right driver. If you choose to not use the loader, the mechanisms by which this happens is all going to be documented, and the loader itself will be open source. So if you choose to absorb that into your app somehow, then you can get a function pointer directly from the driver and jump straight into the driver. But then you have to call the right version of QSubmit for the GPU upon which you're going to be submitting, which is why we don't recommend that you don't use the loader. Most likely what's going to happen if you don't use the loader is that there will be some screwy combination of an Intel integrated with an NVIDIA and AMD discrete at the same time that you didn't think of, and you'll be running on the GPU you didn't think you were running on, and it'll blow up. So yeah, use the loader if you can, and it'll just work.
And who implements that loader?
That is part of the work that's being done by LunaG with Valve at the moment, and it's going to be open source.
Okay,
So
cool. Thank you.
Also.
Yes, symbols.
Do you think you can? Sorry. Do you think you can speak to, once the spec is finalized, what adoption in real-world silicon might look like, or if there's going to be any kind of forward or backward compatibility path for being able to develop apps on this or something like this that still support users who are using GPUs or drivers that predate the standard?
Right. Well, I can't speak to what the other vendors are going to do. We have made the min spec for the API to be roughly equivalent to an OpenGL ES 3.1 device. So that includes things like compute shaders and so on. And that's going to be your low bar on the mobile side. As for the desktop side, we're still trying to figure out what profile or something might look like. From AMD's perspective, anything that can run Mantle can run this API because they're basically the same thing, and we haven't added anything over Mantle that wasn't there before, really. So for us, that's all the GCN hardware. I guess the other vendors can comment maybe, but that's where we'd be.
So Tom, do you want to say something?
Yeah. I just wanted to say we do have this classic problem in the mobile space that we don't control the chain, we don't control installation and update of drivers. As Reese said, it's kind of a pleasure for driver writers to write these and get them working, and we'd kind of like to. We can't shove them, we can't push on a rope. But, well, I'm not going to commit ARM to product plans, but I sure as hell want it.
It seems like if what you've got here is an intermediate language and a series of ways of submitting commands and queues and all that, there doesn't seem to be anything in principle that prevents something from offering this programming interface, but then just running on the the old OpenGL, OpenCL kinds of APIs.
In theory, you could implement the whole thing in software.
Okay.
In theory, in quotes. If you would like to, go for it. I think in practice, you're going to just see the various vendors ship on their latest and greatest, and this is the forward-looking thing.
Okay, anyone else? Yep, down here. Yes. Thank you.
So, question for the guys who are showing the demos. If I understand correctly, SPIR V being the IR needs a front end, and I was just kind of curious, what front end were you guys using for this? Or if you were even using a front end in the first place?
Yeah, so for us, it was originally an ES3 demo, so we did GLSL to SPIR V to our own driver intermediate IR, and then that IR to our ISA. So yeah, GLSL for our shaders in that demo, yeah.
John, do you want to say something? No?
I don't know what they're all using.
Yeah. I mean, so I don't know if you maybe picked up on that, but there is, John and others have been working on an open source compiler front end that takes GLSL and produces SPIR V. I'm assuming that's what you used. Yeah. So that's there now, ready to go, right?
Yeah, that's roughly 3.x functionality. There's probably a bunch of stuff that doesn't quite work yet, but it's a work in progress.
And that's available, right?
Yeah, it's in the Khronos SDK
Right.
place where GL slang validator
So
was
people can
previously.
go check that out right now.
Yep. You say -v and it dumps a binary. You say -h and it makes it human readable.
Okay.
I guess I'll speak for Jesse and say we just faked it. Take GLSL and stick it into the driver, because we only wanted to prototype the critical path stuff that would allow us to look at overheads, the binding model, and the and dispatch queuing and the present.
And Val's demo earlier, it is going through the GL slang validator SPIR V path as well. So, yeah.
Right, next. So I have a question. Tom, you're also chair of the ES working group. Vulkan, you, Shiny, are we abandoning open?
Right, no, certainly not. It is clear that there's going to be a long evolutionary transition while this is happening. And, there's, ask any programmer who's used them, if you have to whip something up quick over the weekend, are you going to write it in this or are you going to write it in GL? I would use GL. So there's clearly a class of applications for which the need to transition to this kind of API is much less than the need to be efficient in your code production. As middleware comes out, of course, it'll get easier. And using, if you don't use the API directly, you may use an engine that targets the API, and that may be the future path you choose to use. But there's a long life for ES. There is, of course, one of the issues that we have not settled internally is the question of how profile structures are going to work. There is a lot of variability. There's a lot of distance in feature space between an ES 3.1 device, although it's pretty capable, and a GL 4.5 device. And the API has to expose that because we have to reflect market reality. So there is, in my view, a role for the ES group to help define what a mobile profile should look like. But all of that stuff is still TBD. We're still discussing.
To ask a beginner's question, looking at Vulkan, how painful is it going to be to write a hello world in Vulkan? Are we looking at 1 page or 20?
I'll take that one. No, so somebody made the joke earlier today that the amount of work to write the code compared to how long it takes to execute the code is just, you would be dividing by infinity or something like that, I think. No, but it's fine. I think John made the point earlier in the Valve talk that it's possible to do a lot of code gen scripting and things like that. So for things you're going to be doing all the time, it's almost silly not to kind of template that out and do it that way. When you look at it, if you try to look at it all in one thing, it probably looks a little daunting. I think our entire test program is about 1,500 lines of code. And that's all of the GLES and all of the Vulkan source to do, not counting the data and all that stuff, but the actual code to render our model twice using both APIs is about 1,500 lines of code. So just rough. It's maybe more than a hello world, but maybe that's what you're looking for.
Yeah.
Okay, thanks.
I have a concrete hello world example. So on classic OpenGL compatibility mode, you do begin, 3 vertices and an end. You just draw a triangle, make sure things are working. The equivalent of that in Vulkan is about 600 lines of code. So you go from 5 to 600. However, you know, you've built a big foundation of which you can build lots of other things. So you reuse a lot of that. But the foundation to do that is going from 5 to 600.
So do you expect there's going to be utility libraries pretty damn fast?
Oh yes, yes, and I imagine a very healthy ecosystem doing that because there's going to be a strong
Right.
need for it. Yeah.
Right. And I think that's actually one of the most interesting things. What is going to get layered on top of Vulkan? That's going to be a very, and we don't know yet. I mean, to see how that evolves as an ecosystem. And an important part of the ecosystem, you know, is tools. Jens, would you like to give us the 30-second summary? Because we didn't talk about tools at all. So could you? Sure. Because that is a related question.
So we're pretty much out of the way in the runtime in a production environment, but having validation layers, having a debugger, these are all going to be critical things for your time as developers. And we wanted to make sure all those tools are available and ready. We're developing them in parallel with the spec and the sample driver and all these production drivers that you've seen today. So they're going to be a first-class citizen and part of this release.
And you can it's a pluggable layer architecture.
That's right. So the entire API is designed with a multi-layered approach. And we've got a layer in there that, multiple layers, micro layers that can check all different validation parameters. We have other layers in there that can check and actually connect to the glaive debugger. So you have an interactive debugging session. And that, and every time we're thinking of what else needs to be done here, oftentimes it's really easy just to abstract that with yet another layer. So we're pretty happy with the way the layer architecture has turned out. Cool.
Thank you. Because I think the utility layers plus the layered tool architecture, you know, it seems like a scary API from first shot, but perhaps it's going to end up not being so scary by the time all the ecosystem stuff is in place. And Tom thanked AMD. I think we also need to thank Valve. Yeah. Because they're really driving. So a lot of the tools in the ecosystem we're working along with Unity. So round of applause for Valve too.
I'm just going to amplify that in this morning's. You saw the thank you slide I put in for AMD. I had one for Valve, and they made me take it out because they're such humble guys. Of course, I didn't tell the AMD guys I was going to do that, so they didn't have a chance. But anyway, yeah, the contribution they made is amazing.
Okay, we have probably time for one, possibly two. Okay, you first.
I'm guessing you guys have discussed this relatively extensively, but it's maybe more of like the philosophy behind this thing. Drivers are trying to handle a lot of like assumptions, just like you put it, and I'm wondering, a lot of the demos that are being shown are very to the point, so obviously they avoid all the assumptions, they can get straight to the middle, do stuff real fast. Engines like Unreal, Unity, Frostbite, whatever, when they start to let you do everything and then throw in the kitchen sink, do you guys think that down the line they might have to take on a lot of the burden that the drivers were assuming, to the point that they might, you know, even though all that driver code is now in their own code and they can fix it and optimize it, whatnot, it might eventually end up being kind of like the inefficiencies that you see in the drivers? Or if you don't, what kind of things do you guys think they might be able to do that the drivers couldn't have done?
Okay. So, no, sure.
Hi, I'm John. I work at Valve. I work on one of those engines. Obviously, there's a concern that we could do inefficiencies, but the reality of the situation is, and I've worked on both sides of this, is that the driver really does have to, it gets these, in a traditional rendering API, the driver really gets these sort of very low-level commands, and then it has to spend quite a lot of effort to try and understand what the hell were you just doing, so that it can make good decisions. The application doesn't have to do that, because it knows what it's doing it. So it's able to make a lot better decisions about when to schedule things and when things are going to be happening on frames that are not particularly cumbersome. There's headroom, and so we should do this now rather than doing it later, whereas the driver just doesn't have that information at all. It's definitely more responsibility for applications. That's actually exactly the point, because it's what a lot of us have been asking for a long time. But it's totally welcome. So.
Yeah, I mean, the other thing I would add to that is a driver, how many OpenGL applications are there in the world ever? I mean, hundreds of thousands of applications, and our drivers have to run every single one of them properly, fast. Otherwise, we get bitched at on internet forums and whatnot for having sucky drivers. And we have to get it right every single time without failure, right? Whereas an application or a game engine, it needs to run the content of that game right, fast. And so even if it's not 100% correct, if it's correct for that application, then it's only a bug when QA finds it, right? So yeah, the surface of a big fat graphics API which does all of this implicit stuff for you is much more difficult, I think, to implement than when you shift a bunch of responsibility up to a higher level where you have semantic information about what's going on and so on.
All right, thanks everyone. We have to break there.